Так, хто у нас ще є? Деніс і Бекшаєв. Ну що, понеслась? Кого першого? Так, спочатку переименовуємо. У нас один. Змінить. Так. Так, Angelsky.
На фоне Чернівецького університету.
Hello, Mark.
Hi, Oleg. Good to see you.
Nice to see you.
And congratulations for getting the meeting to this stage. We're very pleased to be here.
Thank you. Thank you for your participation and the speaker of our conference.
Are you the first speaker, Oleg?
Oh, short speaker
Short speaker, yeah.
our cooperation with our colleague from Taizhou Research Institute.
Yeah, I just wanted to check it was you and not him. Yeah.
Yeah.
Nice to see you, Mark.
Oh, well, good to see you as well, Steen, even if it's only virtually.
No, I have always been only virtual. I'm not real. Have you been in Bornholm recently?
No, unfortunately, my Bornholm friend actually, he's returned to United Kingdom, so I haven't been for some time, I'm afraid.
No. Now I won't disturb you anymore. Looking forward to your presentation, Mark.
Well, likewise.
By the way, you have got a black aura.
Do you not see the back? Do you not see the background?
Yes, but around between you and the background, there is a black aura. Is that something you picked up recently?
Maybe I should look into
your headphones. Good.
Oh, headphones, yeah.
야, 10분 전에 온다면 이 새끼야. 너 빨리 와야 돼. 이거 가져가고 이 새끼야. 그저 아니 진짜. 뭐 하나 임마. 그런 거 네가 좀 하면 좋잖아 이 새끼야. 갖다 내한테 또 바꿔 이 새끼 바꾸면 나한테만 맨날 기다리냐.
예, 지금 누르면 되는 거죠?
뭐 누를 거면 저거 해라. 내좀 처음하고 다 가자.
아, 좀 다 하셔도 돼요. 소리 끄셔야죠.
Let's start.
Okay, so if I may, shall I start then, Claudia? So please let me welcome you to the very first session of the 2023 conference on correlation optics. Even if we're all all of us participants are scattered around the world, our hearts are with you in Chernivtsi. And I did put this background up to try and remind us of our conventional first session in the very historic university buildings in Chernivtsi. So if I may just say a few words, I think just to remind everybody how these Zoom conferences go. So please, please, please keep your mute on unless you are speaking. It makes it easier for everybody else. And if you want to ask a question, please use the reactions button to raise your hand rather than just speaking, and the moderator will get to you. Of course, you can put a question or comment into the chat at any time. If you're speaking, please, if you can, please have the video on as well. Otherwise, you don't have to have the video on, but if you keep your video on, please remember that we are all watching you. So, the first speaker this morning is our conference chair, Oleg Angelsky, who's got a short presentation on the effectiveness of cooperation between scientists of the Research Institute of Zhejiang University, Taizhou, and scientists of Chernivtsi National University within the framework of the created Optical Research Center. So, Professor Angelsky.
Thank you very much, Mark. Dear colleagues, the title of my report about the result of scientific collaboration between Taizhou Institute of Zhejiang University, People's Republic of China, and Chernivtsi National University. The results of collaboration between researchers from the Taizhou Research Zhejiang University and scientists from Chernivtsi National University, who organized the Optical Research Center in 2020, has pronounced significant outcome. The primary objectiveness of this collaboration was to generate and develop influential research direction in correlation and singular optics, with establishing themselves as leading scientific entity in this thematic area on the scientific level. In the picture, you can see the building, the main building of the Chernivtsi National University, and the main building of Taizhou Institute of Zhejiang University here. One of the main priorities of this center was to create and establish a potentially powerful research direction in correlation and singular optics, and gain recognition in the global scientific market as a leading scientific division specializing in this thematic field. We have recently been approached to representatives of the international publishing platform Frontiers with a proposal to prepare and publish two thematic issues in the journal Frontiers in Physics, focusing on our research direction, namely correlation and singular optics and low-dimensional structures, nanoparticles, and optical measurements. You can see this slide. We gladly accepted this opportunity and formed an editorial team for each program, correlation and singular optics, Oleg Angelsky, Alexander Bekshaev, Steve Hansen, Igor Mokhun, Mikhail Vasnetsov, Wei Wang, and low-dimensional structures, nanoparticles, and optical measurements. And Angelsky. We have commenced the process of selecting and reviewing scientific articles. Results we have successfully published 2 spatial issues comprising 7 articles on singular and correlation optics and 8 articles on low-dimensional structures, nanoparticles, and optical measurements. It turned out to be very interesting and fruitful that the peer review process for articles in these journals is conducted openly, and the published works are freely accessible to global scientific community. Moreover, for all articles, the number of downloads and views is analyzed in absolute terms, in numbers, and percentage of views and downloads is compared to the corresponding metrics of all articles published in the 230 journals of the Frontiers platform since its establishment in 2004. Information is provided on the demographics of views and citation by countries worldwide. The percentage of citation for articles in global scientific database, such as Scopus and Web of Science, is indicated, as well as the percentage in relation to the total citations of all articles on the Frontiers publishing platform, which exceeds 2.1 billion articles. Throughout the entire history of the platform's operation, this allows for comprehensive analysis of the demand for articles in this field in the scientific world using both quantitative and qualitative indicators. Therefore, after over 3 years of work, it has become evident that the obtained results are significant, if not attractive. The numbers of early September 2023 indicate that the overall impact factor of this thematic publication amount to 58,500 views and downloads, distributed among 15 publications, 15 papers. Moreover, the impact factor attributed solely to the publication of the Taizhou Research Institute authors stands at 35,600. This figure appears exceptionally appealing. This speaks to the high effectiveness of the optical center's work within the institute. It is worth highlighting the fact that the first review paper by the center's researchers titled Structured Light Ideas and Concepts has already accumulated 14,700 views and downloads, placing it among the top 5% of the most popular articles and top 3% of the most cited articles among nearly 2.1 billion published papers across all scientific disciplines on the Frontier platforms. All of this indicates that this particular research team has been chosen to elevate the reputation of the research institute in Taizhou and Chernivtsi National University in particular. These results you can, for example, these results you can see from this picture. There are articles with view counts. There are articles also with view counts more than 5,000, more than 3,000, more than 2,000, which looks quite in the considering the short analysis period of 1 to 2 years. This is also you can see from if you are analyzing these pictures here, here, and here corresponding. Here you can see the demographics of one of the most popular our papers published in the Frontiers in Physics. Here you can see the demographics and top countries: Ukraine, United States, China, India, and Germany. The high level of recent publication is the high impact scientific journal Nanophotonics by the eminent contemporary physicist Professor Sir Michael Berry. The article titled "Ukraine and Singular Optics" explores the contribution of the Ukrainian physicists to the development of correlation and singular optics over the past 30 years. It highlights the significant contribution of the Organized Correlation Optics Conference held in Chernivtsi, Ukraine. Here you can see the example of this journal. In the distant years of 1980, the Department of Correlation Optics was established at Chernivtsi State University, making it the first of its kind in the world. On a particular level, the idea of metrological evaluation, quantitative measurement of the degree of statistical correlation in structurally homogeneous fields was implemented. The photometric metrology of correlation moments of different orders in the field was also realized. All of this formed the basis for development of quality metrology system for processing surfaces of various natures with sensitivity to high parameters up to 5 angstroms and processing speed up to 1 second. An indication of growing this interest to these topics and our contribution to this growth is the fact that the scientific journal Photonics published the Jade University plans to dedicate one of its upcoming special issue to correlation optics. You can see here. This special issue will cover a range of topics closely related
I think we've lost Oleg. Don't know if anybody can help him reconnect.
I think that we stop with Oleg's presentation and next one.
Okay, so well, okay, we can ask Oleg any questions following
In chat, all questions in chat for Oleg. Okay.
Yeah. Yes, please. There's questions for Oleg in the chat, and so we'll move on to our next speaker. So that is Professor Jung Son from Korea with an invited presentation on Zernike coefficients of digital holographic optical elements. And I will stop you 5 minutes early, Professor Son, so we will keep to the timetable.
Okay. Okay. Well, good morning, but here is afternoon, 4:20 p.m. now here in Korea. Well, anyway, my name is J.Y. Son. and I'm just a professor working for Public Safety Research Center in Kenyang University, Nonsan, Korea. And this paper, my title of paper is a Zernike coefficient of digital holographic optical element. And this paper has several co-authors, and the first one is Tatiana Venkel of this Chernivtsi University, and Bliokh from Italy, and J.M. Rodriguez Ramos and J.G. Marichal-Hernandez of Spain, just La Laguna University in Spain. So the purpose of this paper is just we wanted to show the optical performance of digitally recorded holographic optical element. So we just here, in this paper, I specified as a DHOE via just wavefront. This DHOE was just recorded by wavefront printing method. So comparing wavefront aberration in DHOE with those of spherical mirrors and analog HOE. So advantage, why we are doing just making this DHOE and the digital, holographic optical element, because, when just make analog HOE, we need some kind of optics, real optics. And if you make a bigger and you have very large optics and, larger size optics, and you need just many different, focal lengths, what just focal length you require, depend on. So this DHOE, we're just making DHOE, we considered we can make any size HOE with a desired focal length without using any real optical element. So this is why we are trying to make and HOE with a digitally. By digitally, okay? So the method, we say just the wavefront printing method. So the recording, just the geometric digital holographic optical element, the hologram, is a first actually was presented by in the Jabra Optics in America. And this one is actually Jabra Optics. The Jabra Optics didn't make actually HOE, but they are some kind of hologram itself. So this one shows the holograms, they just generated with a digital recording method. Here, each of this one we called multi-view, and with a camera, and we take all this set of here, and all this here rectangular here on this hologram printing this is we called Hogel, holographic optic element, and this one is actually recorded by image displayed on here, and by just with this one to move, just with this lens, and display this image on this SLM, so special light modulator, and that image is focused on here, and we make some kind of one as a hologram point we record with a reference beam. So this is all this number of images we gave. So this is a different, we call the view images in XY directions. So by doing so, we can make just some of this kind of just a very nice hologram. But anyway, this problem here, in any case, this hologram, the Hogel size is usually 1 millimeter size, and it just gives, a problem of some kind of like that. What? So this is a problem. But in any case, so they are by this way, and they recorded large size hologram digitally. So this method is actually just adapted in just a wavefront printing method. So this is a wavefront printing method, and as this image on this SLM, and the displayed image on SLM is kind of just we made some kind of CGH or pattern of any of the optical element. So this case is some kind of a spherical mirror, just or lens. Okay, this hologram of just a pattern, and so we divided this one some just part here. We just divided 8 by 8. Okay, it's made that way, and with this one and the first part we display here, and we made some kind of here and the record by just as a Hogel point. And in this case, we use this beam and displayed on SLM is use this lens, and this is some kind of a heliocentric lens. So just the image here is not just focused as a point, but they just make some kind of just collimated status. Yeah. So this is we make it some kind of just a collimated way, and we make this kind of just the beam is just not just when you just reconstruct the beam is not appears this kind of way and the diverge, but this coming from just some kind of collimated way. Beam is just this pattern is recovered from here. So we made the doing so, and each this the CGH pattern is recorded here, and this pattern is somewhere this point part here. So by doing so, this pattern is recorded on this hologram, the holographic photo plate we record by digitally, and with this one, and when just we use this reference beam later, and we can reconstruct the pattern here on this plate. It will be reconstructed. So here we used that just SLM is just here. We have Sony and the ELCOS liquid crystal on silicon, and just the 4096 and the 2000 just 160 resolution, right? Having just a very high resolution SLM used, and here pixel size is 3.74 microns, 3.74 microns. So this is some kind of a small wrist pixel size. I think you can find with this SLM now. So this is the HOE, and we made just 4 samples actually with a different and laser beams. And this one is a green, 532 nanometer, just the beam we used, and this one also 532 nanometer, just lasers. We created this kind of DHOE and just holograms here. This is so each of this point is I call it Hogels, but this is part of this the hologram patterns in this in this each of just the holograms, and this one is probably I just listed here around total plate size 5 centimeter by 5 centimeter, and this photo plate is a kind of silver halide, and we used, and this just pattern, okay, hologram pattern was spherical and just a mirror, just or lens. They have the same hologram patterns in any case. So this total hologram, the point here is 51 by 96. So 96, and it is 96 at 51, I think. So they want just made it 5 by just 5 centimeters by 5 centimeters, and this photo plate. And actually, just each spot size is 0.98 millimeter by 0.52 millimeters. So we made this kind of just HOE with that hologram patterns. So these two patterns, if you see that this red line here represent some kind of defect. There are so many defects, some of just 2 of them, and so we just didn't use this one for test, and this one is somehow also this many of this just a red point. So we didn't use this one, and this one even have just a number of defect here, and we used and these 2 and the holograms, and with together with the comparing together with anyway the spherical mirror and the analog just a holographic optical element together to compare their optical characteristics. Well, so one application of this kind of HOE is some kind of just the head-up displays. So right now, well, there's this kind right now there is head-up displays in the modern cars, some just high-end just cars, but they are not using actually holographic just photo plate or holograms there, but they use instead of they have a different method. Anyway, so in any case, the main purpose, we just use some kind of this holographic optical element as some kind of head-up display like this one. So to compare the optical characteristics of these 2 just the digital holographic optics, and we also use here and spherical mirror, and this one has 30 centimeter focal length and this is 15 centimeter diameter. But anyway, this is a 5 centimeters. So we also used only this central parts. So this is just analog holographic optical element. This is actually used in the just combat airplane and this head of displays, and we made it. And you see this one, and this one is working for only just about 530 just nanometer range, the green light only, and the reflect. The other just spectral range is all just transmit. So we can see through this one, and we can see outside and seen, and only just the image, the inside airplane image, we can see through the just green, just here we have green coatings through there, and all this just the information projected by just projectors, we can it's reflected to us from the just the surface, the green coatings from the surface, and the other spectral range just transmit through this one. So this one now, this is people calling about the augmented reality, exactly augmented reality. So you can see both image from the outside and the image and just reflected from your projectors, and you can see just together through this just display just the panel. Okay, so this is just analog HOE. So we just made this for just optical characteristics, and we measured and compared. So what kind of difference each other? So this can just holographic optical element can be used as some kind of this spherical mirror or just a lens. So to do that, first we just to do that. So to measure this one, the characteristic optical characteristics, we should measure the just the most frequently used method is measuring some kind of wavefront aberration from this optical element. So this we actually measured wavefront aberrations. This wavefront aberration, the most the famous method is Hartmann. So just wavefront sensors. So we used that one, and I'll show you this one later. But anyway, so we just this one is we tested actually the focal the spot of this these two digital HOE, and this focal spot here giving here, and another one is giving some kind of elliptic way. So this is somehow circular, but this is about 2.5 millimeter. This one about 4 millimeter. Of this side is about just 2 millimeters, just 2.5 millimeters. So second sample is slightly bigger, and also this is not completely circular. And here you can see some kind of the astigmatisms, and these astigmatisms just coming from because this hologram spot size is some kind of they have just 0.98 by 0.52 millimeters. They have just not exact the same size, so they just giving some kind of astigmatism here. So to measure, I told you that we just designed Hartmann just the wavefront sensor. This is Hartmann wavefront sensor. We used the edge detector. We used here you see the resolution. The Sony mirrorless camera is the resolution 6,000 by 4,000, and the pixel size about around 3.89 micrometers. So this is we used for actually Sony mirrorless camera, and we remove objective, and we put micro just lens array on this one just here. So this micro lens array around just the micro lens array has the micro lens at about 77 by 5, just 51. So micro lenses here, and that just the diameter is 300 micrometers. So we put it in very close because this focal length is about 2 millimeters. We have to put very close to here, 2 millimeters. So you can make the beams coming here and focused on this the CCD sensor of Sony, just the mirrorless camera. So doing so, we just actually we break many of this Sony mirrorless camera anyway. But anyway, we succeeded. Just one of them is we succeeded, and this is some kind of measuring, and we use the collimated beam, and here, micrometer, CCD sensor, and here just we have just samples. Okay, this is just we have just meters or just analog, just HOE or digital HOE samples here, and just diffracted beam we just measured, and near that focused range we put CCD sensor, and we just measure the wavefront of the beams reflect just diffracted from this the elementals. So as you know, this is very simple, but I just wanted to, because some of you may not just know about any of this the principle of this Czech-Hartmann sensors. So when just the beam, okay, this is a micro-range array here, and this is you can say this is a Sony mirrorless camera CCD sensors, and so this micro-range array is our used is about 300 microns diameter, 300 microns. So when the beam coming, just the collimated beam is coming, and they are focusing on the center of this. Okay, they are range center, and this is a focal length here about 2. Just this is we use 2 millimeters. They are focal length. They are just 1 point as a point. So this is a 300. This is a 300 microns, and actually this cell, this is a CCD cell. We divide, and this one 300 micron, and this was 3.89 micron. Just CD, okay, each pixel size. So we can 300 microns. We can put about 770 by 77, okay, pixels by 77 pixels on this, okay, just micro range under this micro range array. So this is the second, also the same. So the second case is just the next micrometers, just the lenses, and incoming beam. They're collimated coming, and they met here some kind of phase shifting materials, just anything, okay, kind of material here, and the beam direction, and so by the phase just shifting, the beam direction is changed by this way. So this beam, and now they are coming just in parallel, just here, just normal to this surface, but now they have received certain angles. They come in this directions here. So now this beam, by this just effect of this materials, they are just focusing slightly, this is just the center here, but they are slightly deviated. So we call this one is a wavefront deviation. So wavefront is deviated by this one. And so by that, we just represent delta x, delta y, and either. So this is delta x, and here we just under this micro range array, and this the CCD sensor we divide on this 77 by 77. We just made it some kind of just quadrant coordinate here. And you see here, and the 38 minus 38 we gave the shift. If just the pointage appear here, we gave minus 38, and here plus 38, and in y direction also minus 38, 38. We just made some kind of this point deviation from this center. So this center is corresponding to this center here. So this center here, okay? So, well, so this delta x, we can just, this delta x is actually the wavefront deviation. So this is given later, and we just have, with this one, we can just wavefront aberration. We can just calculate. But here, when we considered this just path length from here to here path length, and here, okay, focal length. So difference between this just path length and focal length. So this one become lambda, okay? They become lambda difference. This is just the pixel here, and our cases pixel become about 11 pixels shifting. So 1 lambda, okay? Just we use the 532 nanometer. So when this path length here, 2 millimeter, and this one becoming is a 1 lambda, just a 532 nanometer difference it make, and they make, and this delta x or delta y becoming here about 11 pixels difference appears. They are shifting around 11 pixels. So if we make this one as a differences and this beam directions, we cannot make all this, okay, each just you know, the beam directions. We just we just made it some kind of lambda difference. Another next is coming here, and this one is a 2 lambda difference, 3 lambda difference, and such way. And we analyzed later. And this safety, how many? Just micro ranges giving, and the range here and the range here, or range just another place. Okay, so by that way, we just made some kind of our data anyway. So, well, just when you see this is the ideal just focus, you know, cases. And if you consider, as I told, here 1 lambda difference, 11.859. Oh, this is almost 12-point difference. And the 2 lambda difference cases, you can have 16, just you know, the pixel difference. And this is a difference up to 11 lambda, because we have 38. Actually, we have 10 lambda cases up to 37. So the 11 lambda cases, we can have it. So when there this one, the collimated beam coming, this range is about 2 millimeter and 300 microns. The actual, the angles, and here, the total maximum, actually, just angle, just the converging angle is around 4.29 degrees. And the spherical mirror, we have 5 centimeters and about 30 centimeters, and the focal length there, and it's converging, okay? The beam converging, focal port focusing is 8.65 degrees. And the analog whole case, this we have about 50 centimeters focal length. This gives about 4 degrees. And DHO is about 33 or 31 or 32. So they give about 4.6 degree, okay, difference. So actually, here, if you see that this one, DHOE and the spherical mirrors have just slightly in the converging, just angle is bigger than this angles here. So when the collimated beam is coming here, and when the focusing angle, allowed focusing angle to this 8.65 degree doesn't affect anyway. So we can get a very nice and you know, the result, and I can show you later. So one, this is a Shek-Hartman sensor, and you can do, and you can find the Shek-Hartman sensor giving only light spot array. So each micro range giving one light spot. So we have just 6,000 and 300 micron is corresponding to 77 pixels, and we can have here about 77, and this side about 50, just one. Oh, this is we have a 51 micron, just you know, micro ranges. So 77, just 81. But if you see the here, and this part, and some of this part is missing here. So we just remove this pore, just a pore here, and the pore here, pore here. So 8 of them is we removed and only used inside this way. And only this, just the right pattern, only inside we consider buried, okay? Just light spot, we used that one. So actually, this spot array is, if you remove 77 and 69 by about the 40, just this is 51, and just the micro ranges, and if you remove 8 and about just 43. So actual analysis, we used 69 by 43 and the light spot array we used for that purpose. So just after this one and receiving it, we processed it. You can see it here, and each this point, this light spot, and we made it some kind of cell, you know, image here, and the lines, and we made it some kind of cell positions here, and so we can find that just the relative position of this light spot within is a cell here. So we made it that way, and we just analyzed. So this is the way, and the first thing we just have to find the exact location of the light spot in just each cell. So it does give with, you know, delta x, delta y, exact value of delta x, delta y. So this is a very just important process. So to do that, we use some kind of centroid. This is a very just well known, okay, just the centroid problems. So we centralize the problems, it just appears. And here, just shifting from the center, multiply, and each light spot. And, you know, this, well, anyway, this light spot is a nut spot, and they have certain areas. Okay, so when just we used this, our microrange array have just some kind of scale forms, and you can have this kind of diffraction pattern also if you give just collimated beam here and just diffraction pattern, you know. So we can find this point, exact point, by actually crossing over these two diffraction lines, vertical and the horizontal lines. Either or we can find by this way, finding centroid, and we can find either in the two ways anyway. So this is actually our just you know, this is first we tried this method, but anyway, so usually this is a typical method, and we also try to use this one. But anyway, you know, later if you see the part, you know, the edge part of this microlenses, and this light just light spot not appears this way, but very weird forms, you know, scattered many different places. So we have to use some kind of centroid problems. So when this is clear, and these two lines, we can use this cross point here. Edge, just find exact point location of the just light point. So this one, well, actually, if you delta x, you know, x, delta y, and you can find the f, and this one give kind of just aberrations, wavefront aberrations. Why this is just, you know, just wavefront distortion, and given by this one is represented when this one is some Chernivtsi polynomial. So when this one is actually wavefront, actually the aberration to represent this one. So this is some kind of equation form, very complicated equation forms. So first, actually, how we did it, and I told you this is a kind of, well, you can I don't know, you can see that one, and inside you have so just every square, and you can find some the right spot. So if you just magnify some part of here, and you see this one red part is represent the center of this cells. This is 77 by 77 cells, and we find the center, and we find deviations here, and from center to deviation center. This is each. So here with the blue is actually representing kind of just the position we defined from the, you know, find from the two cross lines, the diffraction lines we did. But anyway, you know, some of them here, you know, they have some differences, but actually most of them is very closely matched, you can see here. So by this one, if we find the center and they define, and this position is easily defined, the delta x, we can find the center to here, so delta x. And the delta x, delta y, we can find the very easy anyway. So by this way, we can just find the exact numbers of delta x and the delta y. So what is the wavefront aberrations? Actually, this wavefront aberration is defined as the departure of the extra PP wavefront from the reference sphere. So whenever just we do, okay, any kind of optics, and some of them, they are not exact, actually, they are focused, and we call it point spread function, PSD. And they just at one point, they have a certain size. Some of them just deviate or not. So some of them deviate, some of them just bigger, or something like that. So all this one, actually, that's we consider this reference sphere actually give exact point. The right is focused, that gives the exact point. But of course, there is some diffraction effect involved there, but exact point. But actually, the beam is not exact point, and they have a certain areas. Okay, so they are just actually dot, not the point. So it just makes some kind of dot. So the dot also not exactly circular, but they have some different forms. So that is kind of just the extra pupil wavefront, the departure. So this is a wavefront aberrations they represent. So this one is defined by, so this is the extra pupil, the functions, and here the page forms, and here this is just the wavefront aberrations involved here. So by this one is Fourier transform of actually this x cube, this xy is given. So here we called wxy is a wavefront aberrations, and this wxy are represented by here. Okay, these equations. So this is some kind of by just p rho theta. This is just the polar coordinate. This is a j. So j's component we called Chernivtsi. So to solve this one, and this is already known by this Zernike, and we have to find wj. So this is just coefficient here. So this is our just imminent problems to analyze, to compare the just optical characteristics of this element by finding wavefront aberrations. So with this one have to be found. So this one value is found by this kind of just very high matrix. So we used this one actually. We J here 1, 2, 3, 4. The total 16 values we used here, and this is okay. W1 is this. This is given just from just measurement we can find these values, and this is we consider here. Okay, the A matrix, and this is a B matrix. This is a B matrix, and here we have W with some kind of coefficient, and here. So this will multiply, this one become this one, and it's by equation. So from this is a matrix, okay, some kind of manipulations, and we can find by these forms, and we can find the coefficient by this way. This is a least square method, I guess you know very well. So A, B, and multiply the AT, just the transpose matrix of this one and the A. So if we use this total 16, actually, these numbers here, because we have a X and Y directions, and each X1, we can have a 16, just Y. Each X1 has a 16Y. So if I use here 16 elementals, and actually this part, this lines, number of rows, actually rows becoming 256. Very just large matrix calculations. So we did this is just a MATLAB and giving anyway. So with the MATLAB, we can just did it anyway. So they just give nicely all this just these C values to be calculated. These C values to be calculated. So we use the MATLAB. So well, this is our result, and if you see here, and this is spherical mirror. This is some kind of deviation. Okay, so we have here we have a total 38. This side, this is so here 40, minus 40, 40. Also vertical directions minus 40 and the 40 here. So this is exactly our just coordinate I showed you before, and we just simply plot the point. Okay, by deviation. Okay, and we can have this kind of forms. Oh, this sample also, this sample 2 also same. We can have this kind of positions. And so this is the important thing. So we use the collimator beam, but we have to make a collimator beam. And you see, this is just, you know, the ideal collimate actual beams should focus only one point. But, you know, as a point here on the center. But actually it is impossible to make ideal collimator beam in the laboratory. So we tried many ways, but, you know, they have a slightly different. We can make just you know, slightly all the time slightly different and collimated beams. So they have very similar. Just they have just deviation distributions. But this is actually, you know, about the 10. You know, both sides here. So this side is a 10. This side is a 10. Actually, it's just the deviation. Actually, give only one number. Just you know, the path length difference deviation one. So when the, you know, this collimated beam and this, you know, deviation is, this is actually collimated beam, the ideal collimated beam is have 3 points. So we have to subtract from the, you know, the deviations given by collimated beams. So from here, we just subtract it, you can see very nice, just distributions, you know, in the rectangular and the rectangular distribution in here. So anyway, so this one is coming out, you know, problem here. This is not completely square. So this have, but actually they have just, you know, well, you know, they have just slightly actually rectangular form, because this one is represent definitely. We have here 77 and here actually 51. No, 69, and here 43. So that's why they have rectangular forms. Well, just very uniform, shape. The exactly following this the shape of our, this the cell point, total cell. So if we plot, and this is one plotting, so this is only deviation plot, and this just just only value only we plotted. But when we collected some just the deviations, this case is actually collimated beam cases. I told you they have just about 110. Okay, just the pixel differences. So we cannot make actually. So if we plot the lambda just the differences, if we plot this is completely white. So they just white. They are no just information here. So we in this for this purpose we made it actually each the deviation 2.5 pixel differences. So this is a 2.5 pixel difference. So this is a 2.5 pixel difference, and this is a kind of just squared differences, and we made it. And so if you do that 2.5 pixel, this is a 5.5, just 5 pixel, 7.5. This is giving and 10 pixels, and this is likely 2 more just pixels here. But another cases, and you can have only just less than 10 pixels, just 5 pixels or around 10 pixels. You have a corner, you have here maybe because this distance is different. They are slightly just more actually deviations should be here. But anyway, so you can find this kind of a circular form. This is we call the page maps. So when just use these cases, we just to plot it, show you, and we made it 2.5 pixel just distance. We just collect grouped this deviation point here, and we can have this kind of pattern. So I called this one as a page pattern, color page patterns. We made it. They are circular. Okay. So when you just here use and reconstruct wavefront of this one, wavefront of this one from the Zernike polynomials, if you make it, by that just the calculations we show the matrix, and you can have this one is this cases and this one. But anyway, this form and this form is very similar, but they are just 180-degree rotated form. So this one should be here, and this form is here, and this form is this part here. They are looks very similar in this case. Anyway, so they are only slightly on the differences on this part, but anyway, so they are very similar on the here. So this case is spherical mirror. So this is 2.5 pixel difference, and we made it. And this is a 5 pixel difference we plotted, and this is a lambda pixel differences. Anyway, right? So this is a 2 lambda here. Okay, so we just made this is not just important here, and we have a 2.5 pixel difference, and here lambda pixel difference 2 lambda, 3 lambda, and something 3, 4, 5, 6, something like that. And you can see how they're spread. Their sphericity is very great. Anyway, so and if you see here, just well, this is the one, and just 2.5 cases. And so, this is actually the coming out. This is, I'm sorry, this is, I explained it. This is, anyway, not compensated. So we just didn't use the waveform. We didn't subtract from here, just, the collimated beam. And so this is just the original, just, the wave page, just the original color page map, and just the collimated beam, okay? The wavefront is not just subtracted from here. And even so, and they have a very nice, but this is actually 2.5 and pixel differences, and we plotted here, okay? So when just you make it, and here, well, and just take out from here, and just was that just the collimated beam wavefront, and we can have here very nice actually the collimated beams here. So this is just this beam, and we just made it somehow and you know, the 1, 2, 3, 4 over 10. Okay, this is lambda differences. This one without collimation, without just you know, compensation, we use this one as directly here, just the lambda differences. We can have this one, but when you just subtract from here and just the collimated beam, and you can have this one. So actually, this one, you know, they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost 11. So actually, they have just the entire, you know, they covering all this matter, because this is 8.29 and degree just converging length they should have. They just their collimated, their converged beam covers completely all these pixels. So you can see that, right? And this is only just you know, not compensated by just collimated beam. You can have this part kind of just Zernike polynomial reconstruction wavefront, just reconstructed wavefront. But if collimated, you have very nice and you know, this have some kind of symmetry form of just Zernike, just reconstructed wavefront you can have. So when this just you know, this beam and just compensated just the pattern, okay? If you see the circular, you know, and we do, and they are very, you know, circular. This is you see here. They have just a sphericity is great. This we use the circles and how this the sphericity of this the pattern, and you can see very just you know, well, sphericity is very great, and this almost make a circles here. Well, some deviation here, but you know, they are very good matches. With just either just, they have almost have the circular forms. So this case analog HOE. Of course, this is a 2.5 and the photo comparisons, and this one is okay, just the lambda differences and the compensated, and you know, so actually from this form and you subtract as I told, and this collimated beam wavefront, you can have this part, and this one also. And reconstructed just you know, the wavefront from the Zernike polynomial is also very similar to as you saw previous in just the spherical mirrors. So this is our just the EHOE sample 1, and we have, so this is how just you know, noise here, and actually 2.5 cases is they are just, well, they can still have the color boundaries, but you know, they are just the boundary is almost mixed together. So very noisy. But if you make lambda differences, well, that's just you know, boundaries is slightly better, but still noise here. And this pattern is you know, see that the differences, they have just large differences. Even just you know, spherical mirror is actually compensated, just not spherical. So just collimated beam, okay, wavefront is compensated. They are still very just similar to each other. Just have a big difference here. Well, so this is a sample 2. Sample 2 is just the same and very noisy. And this is actually the lambda cases. They have only just 2, you know, 2 color boundaries almost. But anyway, this is just slightly less the colors, and this is layers. You know, this is lambda difference, slightly different layers they give. Anyway, so this is the pattern. This is also slightly different from the sample 1 and the sample 2 is slightly different to each other. You can see. So in any case, we found actually just the Zernike coefficient from this, and we compared from the just you know, previous metric calculations. If you see here, so DH and here we plotted, and this is we used 0 cases, and the first we have this is only 15. We use the total just 16 element, but first one is actually is just we called piston. Piston is some kind of just flat noise. So we removed that because that value is 0. So we used another just not 0 values we plotted here. Actually, if you see here, and here we just represent some kind of Zernike polynomial form. So here, 1 is a tilt. So your optics is you know, compared to just your collimated in slightly you know, tilt different way, either way, that way, you know, slightly tilt. You can see this way, and this 2, and the 2 is represent some kind of spherocylindrical reflection errors. but this is can be compensated. So this is a 3. A tetraploid is some kind of 3 leaves, and the tetraploid is 4 leaves form anyway. So this comma x comma y comma is on the here, but so this is a generic comma usually, and this part is actually uncompensatable, actually reflection errors coming out this one. So actually you're just the doctors cannot compensate any just aberrations on the here. Okay, this 3 number 3 corresponding to this 4. This is just a spectacle. You are just eyeglasses or your contact lens, and it cannot be compensated on this 3 range here, but only 2 just I get a sphero, just the cylindrical lens, just aberrations you can just correct here. So this is all just corrections we can do. So we did up to here, the report here. So anyway, if you see here, this is a very just unique forms, So this is a spherical, mirror. The values is mostly smaller than other values. But second, if you see here, the green is analog HOE, and you can see, but actually they are actually second. They are compared with average smaller than these values here, if you consider that. So this is not significant this part. I don't know how to use this part, and nobody just explained anyway. So in any case, if we see the spherical mirror, we have here.
Sorry, could you finish very soon, please? You're at the end of your time.
Okay, so this is almost the end. Okay, so they are just very they are just low values here, and compare with the other just coefficient. Okay, different element, they have low values. And the next is just analog, and you can see the DHOA and the DH212 is they're very similar. They're mixed together anyway. I cannot be just any differences. So they are actually, if you consider here the quality, this is the best, and the next here, and these two just so-so, similar. So well, so what is this one? This is I did it. No, okay. So if you compare 4 of them, you can see here, this is just 3 more, just slide left. Okay, so this is a spherical mirror, analog, and if you see DHOA, DH2, and you have this one as a very similar just point, because one is just converging angle of 4.6, it is 4 degrees. This is 8.6 around. So this is very clear and nice. So if you consider even analog just HOE, and this one is compared to this spherical mirror, they are worse than the characteristics. But this is even worse. But they are actually almost the same characteristics anyway. So finally, this is my final just the figures here, and you see here, and I just collected all this Zernike just reconstructed wavefront here, and you see here here sphericity. Okay, this is a symmetry. This is actually represent negative part, and this is a pattern in the actually this is a pattern of this Zernike pattern is 3-dimensional, but actually we just here displayed only in plane 2-dimensionally. So we cannot show you just the negative part, but anyway, negative part coming out of this part here and here, and this is just the plus part and positive part. So they are very symmetry. Okay, 8, and this pattern is a total number is A, and this if you through these lines and this part, this part, this part, this part, they are very symmetrically just related. So second one is just analog, just HOE also the same, but in this case we have 7, and this is 8, but this anyway in these lines symmetricity is very bad here, and they are not very symmetrical. So well, so this is okay, my final slide. So this is my conclusion here, and so far all this result shows that, and the digital just digitally recorded HOE can perform as a spherical mirror, but this quality can be very used for image, right? So projected image will be distorted and the blurred and the noise. And okay, so another thing, so DH are almost the same optical characteristic as the analog, but they are slightly noisier and distorted, because the Chernivtsi polynomial, their symmetricity is actually represent some kind of image distortions. So they are distorted here. The image is distorted. So, well, that's the spherical mirror, of course, just to represent the best optical characteristics. Okay, so this is my conclusion. Thank you. This is all. Hello?
Okay, thank you very much.
Yeah,
So we're running very late now, so we have time for one.
Oh, really? More than 4 minutes?
You run 15 minutes late. So if you can, anyone have a very quick question? Otherwise, we should move on to the next speaker. I don't see any questions, so maybe the next speaker can, so if you can unshare your screen, please.
Thank you. Yeah.
I have a question.
Oh, okay, please.
Maybe particular question. You for the test of your front, you use some metrics of lenses, so conventional Hartmanograms is formed. Maybe the main advantages of your technology of testing is a great number of microlenses.
Yes, you're right.
Yes,
yeah.
But it's known that wavefronts changes smoothly. Can you estimate the optimal number of your microlenses?
Well, you know, I told you this. We used among them, we used only 16 elements. Okay, so
I see.
We didn't use all of them. Okay, so only 16 each.
I see.
Okay?
I see.
Yeah.
Thank
so
you.
That is, we didn't use all of them. Okay, yeah, you know that.
Thank you.
Yeah.
Okay, thank you. So we can always have further discussion in the chat window, but we should move on now to our next speaker is Konstantin Bliokh from Japan and also Poland, and he is talking about topological forms in optical, acoustic, and water waves.
Thank you, Mark. Do you hear me? Everything is fine?
Yes.
Okay, perfect. And I'm very glad to see all of you here online, and great thanks to the organizers for their heroic efforts and these hard times to organize, nevertheless, this correlation optics meeting. And my only wish is to have the next correlation optics offline in peaceful Ukraine and to meet all of you in Chernivtsi in real life. Okay, and also I have to apologize to other speakers that I'm talking from another meeting in Mainz and I couldn't attend even online others talk. Sorry about this. And I will proceed. So I would like to show some etudes and our recent results about topological objects in different kinds of waves. And I will start with, first of all, here I acknowledge my main collaborators on the results shown in this presentation. And I will start with the general introduction, which is probably not needed in this audience, but nevertheless. So if we consider first monochromatic scalar waves and for simplicity in 2D plane and analyze the wave function, then the simplest topological objects are phase singularities or optical vortices as we know them. And these are points of zero intensity where the phase winds by plus 2 pi or minus 2 pi around these points generically. And this L equals plus minus 1, the phase increments in 2 pi units, is called the topological charge of this phase singularity. And if we analyze current, optical current or momentum density in such a scalar wave field, which is given by gradient of the phase multiplied by the intensity, then we can see that this current swirls around such phase singularities, and that's why we call them vortices. In the circular symmetric case, the vortex wave function near the phase singularity looks like in this equation, x plus I Ly. And it's easy to see that this is an eigenmode of the orbital angular momentum operator from quantum mechanics with the eigenvalues, quantized eigenvalue of L. And we can construct localized vortex solution, which are not limited by L equal plus minus 1, but now due to circular symmetry, we can have higher orders, which look in 2D case like Bessel functions with azimuthal phase increments. And we can see that there is a minimal radius how we can localize such vortex solution. The higher is the angular momentum, the larger is the radius of such donut-shaped vortex. Okay, and phase singularities have been observed in very different wave systems, starting from ocean tidal waves, where they are known as amphidromic points. So, for instance, here you can see modern maps of ocean tides, and the left map shows the amplitude of the water elevation in the ocean, and the right-hand map shows the phase of the tide, and you can see many phase singularities accompanied by zero amplitude in, for instance, in Pacific Ocean. And starting from these huge scales to tiny scales of quantum waves, matter waves, electrons, neutrons, and recently atomic and molecular waves. In all these cases, people generated and found a vortex solution or orbital angular momentum modes if we deal with symmetric systems. Okay, and then I proceed with less known results. And surprisingly, but while recently thinking about these vortices and topological objects, I realized that there are almost no works on wave vortices in water waves, and water waves are just the simplest example of classical waves, which we show to students and public, and anyway. And there are no papers on wave vortices in such a simple system. And I found only a couple of works from two groups, one from Australia by Michael Schatz and another from Russia, which showed generation of vortex lattice in water waves. And they used essentially the same setup, just interference of two orthogonal standing water waves in a water tank. And this generated a square lattice of alternating vortices. But it seems that they didn't realize what kind of vortices are these, because what they observed is a kind of non-trivial motion of water particles, of water surface particles, which looks like here. So water particles move along large orbits, like vortex orbits, and at the same time they experience tiny oscillations along these orbits, tiny like spiral-shaped motion. And it wasn't clear why is this so. What's the dynamical theory beyond this motion? So they just reported generation of vortex lattices. But it should be emphasized that these vortices are not the usual hydrodynamical vortices, because standard hydrodynamical vortex is provided by non-zero circulation of the velocity around the vortex center over non-zero vorticity, which is shown in the equation here. But when we interfere water surface waves, for instance, gravity deep water waves, we interfere wave fields with zero vorticity. The vorticity identically vanishes in any linear gravity water waves. And essentially what provides the wave vortex is the quantized phase increment of phase of the velocity, not the circulation of the velocity. And this is very different object. So it's more similar to quantum vortices than to hydrodynamical vortices. And here I would like to make a very important remark, very important for all my talk, is that we usually consider polarization only in optics, like for electromagnetic waves, because they have spin, they have polarization degrees of freedom, and so on, while considering other classical waves like sound waves or water waves as scalar waves. But this is not so. In fact, all classical waves, or almost all, I don't know, are vector waves, and all mechanical waves, which are sound, water, or elastic waves, are vector waves. And their vector nature is described by the displacement of the material particles in each point. So this displacement field, I will call it by capital R, or the velocity, local velocity of the particle, which is just in monochromatic case, minus I omega R. And then in monochromatic waves, these vector fields trace ellipse, like polarization ellipse in optics. And this ellipse corresponds to real space trajectory of the material particles of water or air or whatever. And the generic polarization features of these mechanical classical waves are exactly the same as for electromagnetic waves. Okay, and then so just this year, a few months ago, we posted a preprint. We tried to construct a vortex solution for gravity water waves, and we had to solve a vector wave problem. And so we express displacement of the water surface particle along the Z, X, and Y axis as a function of coordinate. Time is trivial because it's monochromatic and so on. And we found that for any classical waves, water waves, elastic waves, sound waves, and electromagnetic waves, the cylindrically symmetric solution have exactly the same form in terms of the azimuthal dependence. If we choose the Z component to have the vortex of charge L, then X minus IY and X plus IY components have L minus 1 and L plus 1 charge vortices. And this is just a consequence of the cylindrical symmetry of a three-dimensional vector field, nothing else. If you have a 3D field, you have a cylindrical symmetry, then the solution must have this form. And from this, we can find that this solution is an eigenmode of the total angular momentum operator, which is orbital plus spin 1 operator. And it's quantized in terms of L. And this spin 1 operator, again, has nothing to do with spin 1 of photons or spin 0 of phonons, nothing like this. It's just a consequence of three-dimensional rotation of a vector field. Okay, and this picture shows such vortex solution for water waves. So, for instance, the upper row shows the water surface, and you have we have L equals 0 solution, which has maximum. It's not a vortex. It has maximum in the center, and the particle moves up and down, so it has vertical polarization. And the first order vortex L equal 1 has 0 elevation in the center, but nonetheless, the particle moves around along a circle in the center. So it has a circular polarization in the center, and only higher order vortices starting from L equals 2, we have absolutely motionless particle in the water particle in the center. So it's quite interesting. It has some vector features, and the bottom row shows the amplitude and phase of the Z component of the water elevation. And also these white vector fields, which corresponds to momentum density, it shows the phenomenon which is known as the Stokes drift in fluid mechanics. Stokes drift is a slow drift of water particles along the propagation of the wave. And in this case, Stokes drift happens exactly along the gradient of the phase. Okay. And the last year, we made an experiment with Michael Schatz's group in Australia, again, generating a square lattice of vortices, and we observed water particles motion, and you can see that water particles move along circular trajectories, small circular trajectories, which are exactly like local polarization of the vector field I showed. And at the same time, they drift according to the Stokes drift along the large orbital trajectories, which correspond to the momentum density in such vortices. And in theory, equations for local spin density and local momentum density in water waves, they have exactly the same form as in optics. And they just characterize the local angular momentum of locally rotating particles and the global momentum for slowly drifting particles. Okay. And then I would like to proceed with vector fields and the topological properties of generic and homogeneous vector fields. So still, if we have monochromatic three-dimensional vector fields, we can, it traces a polarization ellipse in 3D, and it can be parameterized by A and B vectors orthogonal to each other, which are the major and the minor semi-axis. And as we know, generic singularities on such fields are C points of circular polarization, where the squared field, which is F times F, scalar product of F and F, has phase singularities. So phase singularities of the quadratic scalar field are C points in the original vector wave field. And since generic phase singularities have topological charges of ±1, generic singularities in the original vector field, polarization field, have topological charges of ±1/2. And this corresponds to the pi rotation of the polarization ellipse around the C point. So in three-dimensional case, this was described first by Isaac Freund in 2010. The orientation of polarization ellipses forms a Möbius strip generically, which again corresponds to a pi rotation of the ellipse when we encircle a singularity. And this was measured first experimentally in optics in 2015. And recently we wrote a review with Miguel Alonso and Mark Dennis and analyzed the structures and the geometric and topological properties in generic three-dimensional wave fields. And then Miguel Alonso found this very nice construction that if we represent polarization ellipse by 2 points on a Majorana-like sphere, which was previously discussed by John Honey, then the Möbius strip and non-Möbius evolution of the polarization ellipse correspond to two topologically different types of contours on this sphere. So for instance, if 2 points of the polarization ellipse make 2 different loops, 2 independent loops, then we have a non-Möbius configuration. If they make a joint loop with switch somewhere in the middle, this means that we have a Möbius type evolution of the polarization ellipse around the C point, and this means that this contour in real space encloses an odd number of C points. Okay, and now I would like to discuss how this general and abstract theory can be applied to real observation in sound and water waves. And this recently we made work with Etienne Brasilet and Miguel Alonso, where we analyzed C points and Möbius strips in sound and water waves. And this example shows, for instance, if we interfere just a few random water waves, gravity water waves with the same frequency and different directions, we can have a number of polarization singularities, which are C points in the elliptical particle motion distributions, and around such C points the ellipses form. See it from this animation. So this is real water particles motion in interference of water waves. Each particle moves along an ellipse, three-dimensional ellipse, and C points correspond to perfect circular trajectories of the particle. And around such C points, polarization ellipses or trajectory ellipses form a Möbius strip. Okay. So far, we don't have experiment observing this in the water wave, so it should be feasible. But nevertheless, we have made the last year experiment with sound waves. This was done by Karen Volke Sepulveda in Mexico in her laboratory, and also Etienne Brasilet supervised this experiment. And essentially, it's based on the generation of inhomogeneous sound wave fields using such acoustic metasurfaces, like with spiral shapes, grating, and triangular grating. So effectively, they generated a kind of Bessel beam for sound waves, or 3-wave interference with 3 different directions of K vectors in sound waves. And we measured the pressure and field and the restored velocity field in each point of this 3-dimensional distribution. And therefore, we were able to analyze polarization distribution in homogeneous sound wave field. And indeed, we found C points in the center of the Bessel beam. In perfectly symmetric case, this would be a second order C point. But since we had slight asymmetry, the C points split into two first order C points, and we observed Möbius polarization structure along the contour, which encloses only one of the C points. So these are these vectors of the polarization, like major axis of the polarization ellipse. They are restored from experimental data. Okay, and in the case of three-wave interference, we had a kind of hexagonal lattice of C points. So we could analyze all the field structure around such a first order C point, and we found that indeed it has a Möbius strip topological property. Okay, another generic topological texture which can be found in monochromatic vector waves is a skyrmion. And instead of analyzing elliptical trajectories of the wave field, we analyze instantaneous direction of the wave field, like instantaneous direction of electric field in optics, or instantaneous displacement field in acoustics or water waves. And if in some region this instantaneous field has direction which covers the whole sphere of direction, all possible directions in certain region, like shown here, for instance, in the center, the vector goes down, points down, outside it points up, and in between it shows all possible direction. This is called skyrmion. And this topological number is quantized, so you can calculate it by integral of the vector wave field over a certain two-dimensional area. And we observed, while such skyrmions have been observed in the optics just in the past few years, last year we observed it in acoustic waves. Again, the same experiment with interference of 3 sound waves and directions of the local velocity field covers the whole sphere of direction, and the topological number is quantized. Here, the topological number curve is not perfectly quantized because we had a finite number of points in the real experiment, but theoretical calculations show that it's really like exactly +1 or -1, depending on the phase. Okay, and finally, this is from our recent preprint. The same type of skyrmions can be generated by interfering just 3 water waves. If you interfere 3 water waves, you can have a hexagonal lattice of water wave vortices and also skyrmions as shown here, because the direction of water particle displacement is mapped onto the unit sphere and covers the whole sphere. Okay, the next section of my talk is dedicated to a different type of the object, which we call spatio-temporal vortices. So far, I considered only monochromatic waves, and therefore all topological structures, they were like time independent. But if I now consider interference of non-monochromatic waves, and my wave field scalar for simplicity now depends on space and time, then we can see that phase singularities are moving in such a wave field, moving in the XY plane, which means that I can also plot the singularities not in XY, but in TY plane, in time and space cross-section of this function. And we can see zeros of the amplitude and phase singularities in the same way as in space. And now the question, can we construct a localized wave packet-like solution with such a spatio-temporal vortices in space-time? So this is just to remind you how we construct a vortex solution with angular momentum in 2-dimensional space. We just interfere plane waves with the same frequency with all directions and different phases. And now, if we would like to construct spatio-temporal vortices, we need to interfere waves distributed along such a circle or ellipse in general in the K space, which is shifted from the origin. And therefore, such solution will propagate essentially along the x-axis. So you can see the amplitude and phase distribution of such solution. And importantly, if we plot now instead of kx, we plot omega frequency axis, and instead of x-axis, we plot time axis, we see that this solution have essentially the same form, the same elliptical form as a shape, and it's also phase singularity, also vortex, but now in space and time. And there was a great interest in the past few years to such special temporal vortices because they were generated in a few experimental works. So here is the two pioneering works from Howald-Milchberg group in the United States and from Zhang group in China. Essentially, they used the same scheme using two cylindrical lenses and one faceplate, and sending Gaussian pulses to this optical setup. The output was, depending on the faceplate, the output showed spatiotemporal vortex pulses. So you can see the shape of such pulses, which are like donut pulses, but now in X and time domain, not an XY as we typically use for optical vortices, for stationary optical vortices. So these are still optical vortices, but spatiotemporal. Okay. What we can do in theory for such thing? The first remark is very, very interestingly, such solution, they also bear angular momentum, orbital angular momentum, but now this angular momentum is transverse with respect to the propagation direction of such a wave packet, as you can see from here. And this is a kind of unusual situation. Instead of screw-like phase dislocation, we have edge type phase dislocation, but the phase increment is still 2 pi or integer of 2 pi. But what about angular momentum? How do we calculate angular momentum? Okay, so as I mentioned, you calculate the phase increment or topological charge in the same way, and it's still quantized in space-time domain. The orbital angular momentum is also a universal thing from quantum mechanics. It has exactly the same form, but these wave packets are not eigenmodes of LZ anymore, even if they have like intensity distribution has a circular shape or a donut shape, which is moving. They are not eigenmodes of the angular momentum. And therefore, we need to calculate an integral expectation value of the orbital angular momentum. And there are two important issues when we calculate this angular momentum. First, since these solutions are typically elliptical in shape, we need to modify, and gamma is the ratio of major and minor symmetries of this ellipse. We need to modify the equation for the angular momentum with such a factor, gamma plus 1 over gamma divided by 2. And this is kind of standard thing. The same happens for stationary vortices if you just elliptically squeeze these vortices. But then, and this is what I would expect from such solution. But then it happened that an accurate calculation of the electromagnetic angular momentum in such spatiotemporal vortex pulses yields a very different equation, which is gamma L over 2. And it corresponds to half integer orbital angular momentum in the circular shape vortex. This was first noticed by Howard-Milchberg, and he had some theory for this, explanation for this, but I wasn't satisfied. And we had many discussions and controversies. And eventually, I found a kind of resolution of this paradox. And I would like to notice that when we calculate transverse angular momentum, orbital angular momentum, it's extremely sensitive to the choice of the origin with respect to which we calculate it. It's a kind of parallel axis theorem. So if you have a vortex solution, you have an axis, but if you slightly shift this axis, you will get very different answer because you have a huge longitudinal momentum. So transverse shift of the axis generates an additional angular momentum. And I mean, first choice, we have a symmetric, like elliptical distribution of the intensity, and we calculate, or energy density in optics, and we calculate the angular momentum with respect to the centroid of the energy density distribution. And this exactly gives us this unusual answer, which is a kind of half integer angular momentum. But then this choice is not obvious. We can also calculate, instead of energy centroid, we can calculate photon probability centroid from quantum mechanics. And it's a kind of expectation value of the coordinate operator with the photon wave function in the K space. And what is important, this definition has these omega -1 factors, because the photon wave function is the electric field amplitude divided by square root of omega. This is very important. And when we calculated angular momentum, we had the same omega -1 factors. They are very well known in quantum electrodynamics. And if we calculate this photon probability centroid, we find that it's shifted in the transverse direction proportional to the vortex charge. And if we calculate now the angular momentum with respect to this centroid, we will get exactly the expected value for the angular momentum, which gives us the integer angular momentum for circular symmetric vortices. And the origin of this shift is very simple. To construct the vortex, we interfere different plane waves. In monochromatic case, each plane wave carries the same density of photons. But here in spatio-temporal vortices, each plane wave has a different density of photons because they have different frequencies. And depending on the frequency, you have different density of photons, if we assume the same amplitude, electric field amplitude. And therefore, this results in the shift of the probability centroid with respect to the energy density centroid. And interestingly, this shift, it has a purely relativistic origin. It appears for any moving and rotating relativistic body. So for instance, we have a rotating mechanical wheel in special relativity, and we make a Lorentz transform to the moving reference frame. We can see that the probability centroid, which is determined by the density of spikes in this wheel, is slightly shifted. But the energy centroid is twice as shifted for this rotating wheel, because upper spikes become heavier in special relativity than lower, lower part spikes. And this difference between the energy and probability centroid has a very universal shape, and this is exactly what we calculated for optical spatio-temporal vortices. Okay, and to finish my talk, it's another simple example of generation of such spatio-temporal vortices. It's based on the idea of topological differentiator suggested by, I think, Shanhui Fan from Stanford. And so if we have some surface with transmission or reflection coefficient depending on kx and ky components of the Fourier spectrum of the incident field. If this transmission coefficient has a phase singularity, which has such a form, then from plane wave, we can generate a vortex in the reflected to transmitted beam. And this actually realized near kind of Brewster angles in usual dielectric surfaces. So if we need to construct spatio-temporal vortices, we just need to find the metasurface where transmission coefficient has a phase singularity in omega k plane instead of kx, ky. And this is the idea of Zhichao Ruan from China. And in collaboration with this group, we realized such a metasurface in acoustics, which indeed shows phase singularities in transmission coefficient in the kx and frequency domain. And by sending a Gaussian pulse with parameters matching this phase singularity in omega k plane, we were able to generate an acoustic spatio-temporal vortex pulse. These are results of the experimental measurements. So it's like a two-dimensional problem, like a two-dimensional waveguide when we send Gaussian pulse, and in output we measured spatio-temporal vortex pulse. This method is topologically robust because the phase singularity in the transmission coefficient cannot be removed by any perturbation. Therefore, if we even put some garbage, some random scatterers in this metasurface, still the phase singularity is there. It can be adjusted, but still this metasurface is very robustly for generation of acoustic vortices. Okay, I would like to finish with this and just summarize my talk that I described vortices and phase singularities in water and acoustic wave fields, and also polarization singularities in Möbius strip structures in acoustic and water wave fields, and also skyrmions. And finally, I described spatial-temporal vortices and their angular momentum properties and generation of acoustic spatial-temporal vortices. Thank you very much.
Thank you very much, Kostya. We have some, although we're a little bit late in the session, we do have some time for some questions if anybody would like to ask.
Sure. Please.
Mohun have a question. Konstantin, can you propose more number of examples when, without experimental tricks, we can observe the space-temporal vortices in nature?
Yes, very simple. If you interfere three plane waves with different direction and the same frequency, we generate a lattice of usual vortices, as we know, right? Now, if you just slightly tune frequency of one of these waves, you will have a moving lattice of vortices.
How?
And this will be spatial-temporal vortices already.
How we can change the frequencies?
Or a frequency tuner, whatever you have in your equipment.
Okay, thank you.
Or even you can double frequency with some nonlinear converters, whatever.
I see. Thank you.
Konstantin, maybe I can ask a question. So you were talking about this conserved quantity associated with spatio-temporal vortices, and I was wondering, presumably it's related to the invariance of the mass moment. You know, when you're thinking about the conserved quantity associated with Galilean transformations, which is what you get when you generalize Noether's theorem to space-time. So angular momentum is what you normally would conserve in just space, but if you include time and space together as and look for the conserved quantity there, you see something very similar. And I think depending upon whether it's Galilean or Lorentz, you maybe have these two choices that you talk about.
I didn't mention conserved quantities, but if we are considering conserved quantities, okay, you have angular momentum tensor in space-time, which include angular momentum and boost momentum components, and they are conserved. So I think in our optical applications, we still have the same conserved quantities as for usual spatial vortices, but we just need to calculate them more carefully. This is my point.
Right, but I think I would suspect it'll be very close to those centers of momentum that you talk about as being those conserved quantities if you looked at the Lorentz transformation or a Galilean transformation.
Well, Maxwell equations are obviously consistent only with Lorentz transformation, right? By just intrinsically. By their form.
Yeah, but you're looking at the kinematic, so I would think that there may be a version for both.
Yeah, in principle, yes, because for instance, we constructed the same vortices for Schrödinger equation where there is no Lorentz transformation, and then there is no such problem which I described. Then everything is equal, and there is no relative shift between the energy and probability.
Right, exactly, and that's what I'm saying, that there'll be one for both Galilean and Lorentz.
Yeah,
and that's what you're saying.
Right. I agree with you.
Okay. Thank you. Anybody else got any questions for Kostya?
Yeah, I have one question. Okay. Hello, I have one.
Yes.
Okay. I saw you are just water, wave vortices, just experiment. So all this movement inside you just draw by the arrows. How did you actually experimentally just measure that one? I don't know. This is how did you get all this one? Yeah.
You mean this water particle trajectories?
Yeah, trajectories, and you draws, these figures there, and the arrows. How did you actually experimentally move it?
Okay, so there are methods in water wave experience. For instance, they put on water surfaces some powder, some dark particles, and then they image it with cameras.
Yeah.
And these cameras, if you have like three-dimensional image and you can just record with your video cameras, you can record three-dimensional trajectory of your water particles. Of course, there are many experimental challenges in some experiments. And here, for instance, in these experiments, we were able to trace particle over like 5 periods, like 3 to 5 periods of oscillations only, but this is sufficient for our goals.
Okay, that is, well, just we actually I used the previous and, you know, just the laser Doppler, just the velocimeter to just make directions and velocity change, you know. Yeah, but now I don't know, this is your camera and the particle method. Of course, we put some particle there, but is it just deep? I don't know how deep you can just measure actually. You only surface?
Only surface,
not surface. Not okay.
Yeah, all the pictures I showed only for surface particles. Yes.
Okay. Thank you. Yeah.
Welcome.
Right. Yeah.
If there are no other questions, then let's thank Konstantin again.
Thank you.
And so I think our final speaker this morning is Sergei Odoulov, who's going to be talking about two-beam coupling in low symmetry crystals and how it can be optimized. Sorry, Sergei, you're muted.
Oh. Can you hear me? Yes. Good.
Now we can. Yes, thank you.
Thank you for your introduction. And before to start with our science, can you switch on? Yes, right. Make it in full screen. It's here. Here. Here, where? Yes. And before to start with our science, let me thank all participants who decided to make this flow of conference in Bukovina, in Chernivtsi, not interrupted by very deep singularity. So I hope that next time we will see each other in person, but I'm very happy to see many faces which I know for years, even in this type of conference when we are quite far away from each other. But I see that Professor Denis is nearly in Chernivtsi. It's sitting near the residence. How it happened, it's mystery, but it can be solved. So, beautiful country of Bukovina you have seen after the conferences, and you know how it looks. Residence you have seen so many times. So you will hear today my presentation, which is in flow of what we were doing for years, investigating the different kind of photorefractive crystals. And you know that in principle, photorefractive crystals, the definition is simple: photoconductive crystals lacking the symmetry center that allow for recording and storing the index gratings. And both things were sufficiently successfully done in the past. In the mid-80s already, in Hamburg, Professor Kreutzig and his co-worker Kurz created first optical memory. In 1 cubic centimeter of lithium niobate, they were able to record and register all telephone book of big city of Hamburg with 100 pages. And approximately 2 years ago, I myself was able to see that it's still existing. It's not vanishing, and it still can be used. So the storage material, the materials for storage, this is one aim of photorefractive materials. But much more important from our opinion is the application of photorefractive materials for different real-time operations, like amplifications of time-varying beams, generation new beams, phase conjugation, processing of information, etc. In this case, in second case, the main parameter is the gain factor, coefficient of amplification, which is directly proportional to index of refraction change. And in first situation, we have the same parameter but squared, because diffraction efficiency is proportional to the square of delta n of refractive index change. So the problem, how to improve, how to make larger these two parameters, was always actual problem, because for storage, the volume of storage will depend on how many holograms we can record in the same cubic centimeter. And for the dynamic purposes, it is important too. And here you can see the expression for gain coefficient. And you can see that the main parameters which define the value of gamma is effective electro-optic coefficient and the product of refractive indices. And in principle, there is here in denominator the epsilon dielectric constant, which enters here through the device screening length. And let's have a look for what we can do with R effective in different materials. This is only for short history. The cubic photorefractive materials have three components of electro-optic tensors, and they are nearly, how can I say, isotropic in a sense of other values like index of refraction and dielectric constant. But even in these materials, we can improve gain factor by choosing particular orientations of our gratings. It's still the case in lithium niobate crystal, which has a little bit larger electro-optic coefficients, and that's why it was much more frequently used for optical storage systems. And the best from these three is barium titanate, which has more than 100 picometer per volt electro-optic coefficient, but it also has a special standard situations for using.
The slides don't change.
Excuse me?
I think, Sergey, that the slides don't change when you talk.
They're not moving on.
Excuse me, I couldn't understood here.
I think the slides don't change on my screen at least.
And now can you see the changing slides?
I only see the Outlook slide.
No change.
Oh, sorry. This is technical problem.
Just reshare your screen.
I think you must switch to full screen mode.
To which one?
I think now it's okay.
Yes.
It should be fine.
Why it changed?
No, but now it's not changing in my machine. Good. Excuse me. This will take some time, but can we return to my screen? No, for the screen of computer in order to switch it on directly. And one more time. And can you see now the full screen?
No.
Ні.
Тут написано.
Вони не бачать. Там вже проблеми.
Вони казали, що вони не бачать тільки, що вони змінюються.
А тепер бачиться.
The question is, can you see now screen?
Yes.
Yes.
we see.
Yes. And full screen too?
Yes.
Yes. And now, is it changing?
Yes.
Good, wonderful. I'm very sorry, I'm not very experienced with this technique. So I will miss a couple of these slides showing what can be done with lithium niobate and barium titanate and how to optimize gamma in these crystals, because I lost some minutes. But the most important thing which I intend to discuss today is that a part of photorefractive tensor itself, which is the defining gamma factor, we have here also index of refraction and this dielectric constant in denominator. And playing with them, sometime we can get a good increase of gain factor. If we will play with crystals of best symmetry, of centrosymmetric, of non-centrosymmetric cubic crystals, you see we will have all refractive indexes identical and all dielectric constant components identical. So any additional shift back and right to the left of direction of grating recording will not affect too much the result. But in lithium niobate, in barium titanate, we can have a small, relatively small contribution of these additional factors, which can improve a little bit, but not too many, not too strongly improve. And in stannum 2p2s6, which will be the topic of my talk today, we have a very complicated situation because crystal is biaxial. Its electro-optic tensor possesses 10 non-zero components. Its dielectric tensor possesses 5 non-zero components. And if we will compare, for example, the standard orientation when we are using the largest electro-optic coefficient with all three indices identical, with slightly tilted configuration, we can show that we will get advantage in gain factor, and this advantage is not negligible. But first of all, to play with this, we needed to know exactly the we needed to characterize this crystal, because the sources that we were able to find in literature were giving quite contradictory results to us. Even for electro-optic coefficients, sometimes the signs were shown not correctly, sometimes the values. So it was necessary to us, first of all, to make measurements to ourselves. And this, what you see here, is just our own measurements. The second thing, we intend to play with dielectric constant, epsilon. And here the discrepancy was huge. You see, in one source, you can see 460 for epsilon xx component, and in the other case, it's nearly double, nearly half of this value. So this was necessary to us also to measure this tensor. And fortunately, this can be done with our dynamic holography. because one of the parameters of dynamic hologram is the speed of response, the recording time and the relaxation time. And this time is, in fact, time which is defined by very simple expression that it will be epsilon naught in numerator and constant of photoconductivity in denominator. So we can measure the recording time as a function of rotation coordinate for such an orientation of a crystal. And we can plot a curve which will show to you obviously that the maximum of this distribution is tilted with respect to OX axis. What is the consequence of this non-zero, non-diagonal component? And this non-zero component in this particular case is positive. And this was our aim, to know whether it's tilted in one direction or it's tilted in the other direction. You will see why it's important. This was how we did it. We were measuring angular dependencies and compared with our calculations for two possible signs of epsilon, and much better coincidence you see for black and red curves than for these dashed blue curves here. Now we are sure that this sign is positive. Now let's have a look what we can expect when we are recording gratings in three different cuts of crystal. The first column, it is X cut, the second Y cut, and the last one is Z cut. Let's start with this Z cut column. We have refractive index change, which is plotted here, and you see that this section of ellipsoid is symmetric with respect to the x-axis, and with the largest value here. We have the epsilon that we measured in this for this orientation, also symmetric with respect to the x-axis, and also with the maximum axis. And when we are trying to measure effective electro-optic coefficient, we also obtain the same result. The largest coefficient is along X, and this is a simple, it coincides with R111. So this can be like a reference value for us. When we are recording a grating with such a cut of a crystal, we will profit from the largest electro-optic coefficient, and we will have a certain reference with which we can now compare the possible recording in other orientations. If we will have a look for first column, so small value of electro-optic coefficient immediately say to us that there is no hope to get here any advantage with respect to this one. And all other parameters like R and N, they are not impressive too. So the only hope to do something better than for Z-axis, it was to use Y-axis. As you can see, the ellipsoid section is tilted to 45 degrees, so the maximum value will be not at all along X direction, but approximately at 45 degrees. The epsilon curve is tilted, you already know from our own experiments, and our estimations for effective electro-optic coefficient are shown here, that for one normal way, we have a curve which is tilted down, and if you will compare the value of this effective electro-optic coefficient, it's larger than in this case. Here, I don't know whether it's well visible. There is a unity curve. And this unity, it's exactly what we had here. But as you can see from this slide, the effective electro-optic coefficient can be much larger. It's maybe strongly exaggerated, but considerably larger than this unity. So using this unusual cut of a crystal, we can get advantage in gamma coefficient, in coefficient of amplification, or in a gain factor. This is expression, general expression for maximum gain. And what we have here? N cube is coming from this measurement. From this measurements, we have R effective, and here we have epsilon, which is following from this experiment. This is Z cut, which is a reference cut for us. And if you will see the final expressions for gamma, you will see that the only one largest electro-optic coefficient is enters in this expression, and this gives this largest value, which is equal to R111. Let's have a look now for Y cut simple. Here the situation is more complicated. You see the expression for R effective contains three different tensor components before in brackets before cosinus beta, and three other components in brackets before sinus beta. Fortunately, these two are both negative, so, and this is positive. So the altogether it becomes much larger than R11. And here it's the same situation, but with opposite sign. If we will have a look what it gives as a result, you will see this blue line. In case of 0 beta, we have a largest value of this bracket. But if we are deviating for a small angle from this 0, cosine is changing not too strongly. But on the opposite, sinus will be growing very quickly. And this term will improve us the situation, giving larger gamma effective comparing to gamma 111. Also, you see that the epsilon which enters in the denominator of these two curves is changing, but is changing not too strongly in one direction, but quite strongly in other direction. And this means that it is also helpful for getting larger gain coefficient all over. What we were able to do, we were trying to construct some technique which allows us to take into account all these tensorial properties and to combine them in such a way that if we are choosing a certain direction of bisector between two recording beams in the 3D space, we can calculate gamma factor analytically. But by hands, it's not quite difficult to imagine how it can be done. So our final decision was that this was made numerically, and with special programs which is called, if I'm pronouncing correctly, DGEEV of a package LAPAC. And this allowed to us to plot two carpets in polar coordinates. This is theta and phi in such a coordinate systems. And the colors here are showing to us how large can be effective gain coefficient. 0, this is the only one direction along y-axis, perpendicular to this plane. And you see that for this direction, we have a pink color, which means that we have largest possible gain from all of possible directions, different directions in this 3D space. And this largest value is, comparing to xxx value, 1.5. So 1.5 times we can improve gain factor when choosing the direction of bisector along y-axis. But is it the only possibility? And our calculations show that that's not the case. If we will take, for example, this theta angle 55 and phi angle 42, we will come to the optical axis direction. And between 0 direction and between optical axis, we have still the same pink color. So all possible orientations of our bisector of two recording waves, in this case, will give to us a big advantage with respect to the standard orientation of a grating. What happens when we are crossing optical axis? The smallest electro-optic coefficient becomes larger, the largest, and we inverse the situation. After that, if we are continuing in the same direction, keeping the same polarization, we will get smaller and smaller diffraction efficiency. But as you see here, there is plots for two possible refractive indices, for fast optical mode and for slow optical mode. And just in this point of optical axis, when we will switch for other index of refraction, we will still have very high diffraction efficiency and high gain coefficient. It's better to show it in such a way, cutting unimportant parts. Here we are going this way, here we are continuing this way, and always we are in this preferable color of largest possible gain. What does it mean in 3D space? That if we will have a look, the two optical axes of this biaxial crystal give us so-called optical plane. And for any direction of bisector of recording beams, which is going through this optical plane, we will get very high diffraction efficiency and very high gain coefficient. And this was the main result, which we were able to prove experimentally. So what we did, we took y-cut sample with such a coordinates in this phi and theta space. And for this situation, we started to change the angle of between two beams, changing the spatial frequency and therefore changing the value of measured gain factor or measured diffraction efficiency. You see, this is shown by this theoretical curve or fitting curve and this experimental points. And in the same graph, I show the value which we can get in standard orientation of Z-cut crystal when we are using only one electro-optic coefficient R1, 1, 1. And you see that the experimental points here are obviously higher than this level. And it approximately corresponds to our prediction so that we can have advantage 1.5 times with respect to the standard orientation. Now, you can ask me whether it's not simply some zoological study which is for nothing. That there is infinite possibility to change different directions, and sometimes it's better, sometimes it's worse. What will be my answer? If I will take here not the gamma factor, which is larger than this green line, or here in this case, it does not tell to you too much. But if I will take 1 centimeter thick crystal and will work with such a gamma, I will have for green level the 20 times increase of intensity of a big beam. But if there is this improvement and we are working with the highest gain factor which we get here, we get immediately 80 times, approximately 2 orders of magnitude amplification of a weak beam. So it's really not simply the toy, and it can give a real advantage. And before to finish my talk, I intend to thank the people from Uzhgorod State University, who for years were supplying us with the crystals which they are growing in the laboratory not far away from this church. Here is physics department, and here is the place where all our crystals were grown. Thank you very much for your attention.
Thank you, Sergey. Does anybody have any questions?
No questions.
Oh, I have one question, okay?
Yes, please.
Can I? Yeah. So you told about this photoreflective crystals today, and this SN2, I don't know exactly just what the name of this crystal. So this one can be just have a better, you said, the diffraction efficiency than just the barium titanate or lithium niobate, other photoreflective. That is what you talk about?
What were the parameters for our crystal? First of all, it has very long name, TiO-D phosphate, but no, its formula, it's stannum 2P2S6. And what about diffraction efficiency? Depending on impurity, which is, and depending on technological process, we can get very high gain. for so-called brown crystal, we have a gain factor up to 60 reciprocal centimeters. Unfortunately, the technology is not yet very good for producing this crystal. And what the regular non-doped crystals, they can have 10 reciprocal centimeters in for red region of spectrum, for helium neon laser, and they can have approximately 6 for infrared, for 1.06. This is the importance of this crystal, because it can be used until the optical communication wavelengths. 1.3, it's still sensitive, and when doped, it can give gain coefficient approximately 8, even 9 reciprocal centimeters.
Okay. So anyway, you said that this is just for what's the dynamic holograms you display on there. So
I did not show the dynamic hologram, but
yeah.
What I can tell you is that apart from diffraction efficiency, that it's rather very quick crystal, quick response crystal. That the relaxation time, or not relaxation time, but the build-up time of a hologram can be a fraction of a second. And so you can work with moving in time images where any frame is a fraction of a second.
Okay. Okay. Yeah. Thank you. Yeah.
Thank you for your question.
Thank you.
Any more questions?
I have a question.
Yes, please.
Sergey,
I can't hear you.
I think we've just lost Moken.
Excuse me for this joke. This is very good. That not only me myself, I have problems with this system.
I think we've all forgotten how Zoom works, having now the pandemic is over. We have Moken back.
What? Moken back. So you know.
Yes, this means that the next conference should be in Chernivtsi.
Does anybody have any other questions while we wait for Moken to return? I don't know what. That's some discussion in the background. Do you have any other? Yes, Moken, we lost you. Could you start again, please?
Some technical problems. Sergey Georgievich, can you repeat about the reaction time of your refractive medium, and what the minimal reaction time you can propose?
The build-up time is photoconductivity time, and we can go to millisecond range if the intensity is high enough.
Okay.
So with He laser, it will not be maybe possible, but with Krypton laser, it's wonderful. With millisecond range response. But this is build-up time. If you are recording a grating, in principle, to erase completely, you need to wait longer. because there is a slow grading which is developing in addition. But if you are changing, permanently changing image, this compensation grading doesn't show up, and you can change with really 1,000 times per second in your images.
Okay, thank you. And the second question is, usually you eliminate your crystal by constant intensity. What will be happened if we illuminate by, for example, matrix of optical vortices, or even space-temporal vortices? Can you obtain some new results in this moment, because we have the inhomogeneity by angular momentum of in the operation plane?
I must say that it's difficult to answer to me, but maybe we can talk about such a project, common project.
I see. Thank you. Thank you. Thank you. Thank you.
Okay, thank you very much. Any more questions? If not, then let's thank Sergey again, especially in the difficult technical circumstances. And so yes. I think we will reconvene in 1 hour and 35 minutes. Whatever time zone you're in, that would be I think 2 p.m. in Ukraine time, but different in other time zones, of course. Do any of our organizers have anything to they want to say before we break for lunch?
Thank you very much. Now we have a short break, a long break, and at 2 p.m. we start our second plenary session. And please note that we change links from one session to another. This moment must be taken into consideration. Thank you. See you soon.
Thank you. Good. По-моему, я закончил на 10 минут раньше.